Hello, everyone. My name is Grace Idowu, and today I will be talking about method development for analysis of polycyclic aromatic compounds in environmental samples. This research was carried out at the Center for Oil and Gas Research and Development at the University of Manitoba. Polycyclic aromatic compounds are common environmental contaminants. The most common of this group is the polycyclic aromatic hydrocarbon. Here I'm showing you the simplest member of the group, naphthalene, which has a two-membered ring. On the naphthalene ring, we have 8 different positions that are available for substitution. These positions that are available for substitution give rise to various polycyclic aromatic compounds. An example that I'm showing right beside naphthalene is alkyl polycyclic aromatic hydrocarbon, where a naphthalene ring has a metal substituent attached to one of the positions. And as we can see, we also have a polycyclic aromatic sulfur heterocycle where a heteroatom, in this case sulfur, embedded or is embedded in the ring of PAH. Also, we have halogenated polycyclic aromatic hydrocarbon. In this case, I'm showing a 910 dichloroanthracene where 2 chlorine atom is attached to the backbone of an anthracene ring. With these various positions are available for substitution, we have various isomers of alkyl PACs that are possible. Here I'm showing you for naphthalene and phenanthrene, naphthalene being a 2-membered ring and phenanthrene a 3-membered ring. As we move from C1 to C4, which is the number of substituents on the ring, we can see an exponential increase. On my y-axis, I have the number of isomers, and my x-axis, the 2 compounds being evaluated. My colleague in the lab was able to come up with numbers of theoretically possible isomers for substituted polycyclic aromatic compounds that are environmentally relevant. As we move from C1 to C4 in naphthalene, we can see an exponential increase and a similar trend observed for phenanthrenes. Although these are theoretically possible isomers, this explains the complexity we see in environmental samples when they are being evaluated. For my method, I used the Eurochem guide, and my method was validated to fulfill 8 method characteristics, which includes the selectivity, the LOD, the LOQs, the sensitivity, and the working range. Also, I use standard reference material to check for my accuracy and precision on also method uncertainty or the measurement uncertainty, and also the ruggedness of my sample processing method. For my method of quantitation, I use the isotope dilution for PAHs, where response factor of the native PAHs was compared to authentic deuterated PAHs. For the alkylated PAHs on the other side, I use 2 approaches for quantitation. In situations where I have individual alkylated PACs available in the lab, I did an individual quantitation. And knowing that we have a whole lot of these isomers of alkylated PACs that are possible, I also did a cluster analysis for the quantitation. During my method development, I checked and used various modulation time and temperature ramp rates to be able to arrive at a method for my analysis. One of the focus of my analysis is to do individual compound identification as against a group cluster identification that is common when it comes to 2D analysis. One of the goals is to be able to use this individual separation and identification of compounds for forensic fingerprinting or in ecotoxicology assessment. On the top panels, I have the fast ramp in 2 seconds modulation time and in 5 seconds modulation time. The bottom panels shows the slow ramp in 2 seconds modulation time and in 5 seconds modulation time. And as I'm showing here, the slow ramp at 2 seconds modulation time give rise to individual separation. And in this case, this is a C2 naphthalene from a coal sample. I have over 45 in-house mix of alkylated PACs that was gotten individually and then mixed together. I recently included some nitrogen-based PACs as well, because I'm currently expanding my standard base in the lab. Here is a contour surface plot of our collated PAC standard. And with the standards, I could even see the separation of a 3,6-dimethyl carbazole and a 1,7-dimethyl phenanthrenes. Although these can be individually mass resolved, but we can see the separation that is obtained in 2-dimension mode. On this slide, I'm showing you the C2-phenanthrenes anthracenes profile for core sample and also for standard reference material 2974A, which is a muscle tissue. We can see the separation that was obtained for the C2-phenanthrenes and anthracenes present in both samples. A take-home from this slide is the pattern identification that our high resolution time of flight was able to provide. Here we can see that the first two compounds that was noticed in the core sample isn't a dimethylphenanthrin, but an ethylphenanthrin. Whereas the compounds, or the first two compounds that were observed in standard reference material 2974A, which is the muscle tissue, has what a mix of the dimethylphenanthrin and an ethylphenanthrin. And this is one of the goals of this research, to be able to do some individual identification, to be able to check for patterns as against just using the regular diagnostic ratios that we've been using so far when it comes to environmental forensics. For my method performance characteristics, I'm showing you some result for the working range, which is between 2 to 10,000 picogram per microliter. The linearity shows higher than 0.99 in all cases. And my detection limit, which was done in 1D mode and in 2D mode, were comparable for the pHs and the APHs in the two modes that the GCGC was run. Here I'm showing you the result from a standard reference material. We checked for the accuracy and the precision. On my y-axis, I have the concentration in nanogram per gram and 4 compounds that are being evaluated. The gray bar is the certified values that was presented in the certificate of analysis. I also did similar analysis on a triple chord, which is the GCM-SMS. I have the results in GCGC 1D mode and in GCGC 2D mode, and we can see that these results are all comparable. This method has been used to elucidate halogenated polycyclic aromatic hydrocarbon in the Canadian environment. We've been able to use it to identify 3 HPAHs in samples from the Alberta oil sands, this being the first to be reported in the region and also in Bowder in Canada. At the moment, I'm working on some tire rubbers, some coal sealant, from coal tar and asphalt sealant to be used for identification of patterns in environmental samples. Currently, I have the tire rubber and the asphalt sealant, which I'm showing on the screen, and we can see the activity showing here for the C2, or for the phenanthrenes and the anthracenes. We can see the presence of just 4 of the phenanthrene groups in the tire rubber, and we can see the presence of a 2-methyl anthracene right at the middle of a C1 phenanthrenes. We can see more compounds present in tire rubber for the C2, C3, and the C4, and we can see a decline or a decrease in asphalt sealants. These reports, or the profile that will be gotten from these samples, will be used to identify input in environmental samples, which includes sediment and powder. In conclusion, my method has been validated using the ERAChem guideline and found fit for the purpose developed for. The 2D method is used for individual isomer separation and while having a unique compound class identification known for importance in forensic studies. The 2D method also has been used to elucidate halogenated compound in environmental or in the Canadian environment. And this also is being used currently in assessing some toxicology work or risk. Also, this profile obtained from the coal tar-based product from tire rubbers and sealant will be used for further fingerprinting in sediment and powder samples from the Canadian environment. Thank you very much for listening to my talk today.